Hello. Hi, everybody out there. This talk is going to be about the future of C++ parallel and concurrency safety guidelines. My name is Michael Wong, and along with my colleague Ilya Burylov, we're going to show you where the safety and concurrency guidelines for parallelism and concurrency is going to head towards. First, a little bit about my colleague Ilya Burylov. He'll come on the camera soon, or when he comes to talk. He's a principal engineer at Intel, and he's been an architect of C++ software solutions for autonomous driving markets, with contributions into functional safety, into MISRA standards, and contribution into SG1, WG21 in threading, vectorization, and numerics, as well as contributing into SYCL, the heterogeneous C++ programming language. A little bit about me. I'm a distinguished engineer at CodePlay. I'm the chair of SYCL, Heterogeneous Programming Language, as well as chair of the C++ Directions Group. I've been involved in C++ for a long time, as many of you guys probably know. But I've been interested, spanning a career from high-performance computing. I was the previous CEO of OpenMP, to today doing a lot of work in terms of autonomous driving and safety. So a lot of this talk comes from our collective experience in that space. I'm also the chair of SG19 on machine learning and the chair of SG14 on games, low latency, finance, embedded. Many of you guys out there know me, and I really enjoy knowing you guys and been working together with you guys on many of these things. So a bit of an acknowledgement, of course. A talk like this spanning many disciplines cannot happen without the help of so many people. And we're going to be using some images. They'll have their own copyrights. We're going to have company logos, company products from other companies, and we want to acknowledge their rights as well too. But there are going to be any remaining errors and stupid mistakes. Those are all ours. So we're going to talk about three things. We start with what if you can't test everything? And then we go on to try to answer partially the question, is C++ core guideline or MISRA C++ enough for concurrent safety? And then finally, we're going to talk about the work that we've been doing as a group for the last 2 years on heading towards safe concurrency standard. This is actually the first time we've revealed this. We've had a collaborative group for quite some time. So let's start. So many of us here are engineers and computer scientists. And of course, as engineers and computer scientists, we have absolutely been trained to test everything. We have so many different kinds of tests. It's a major department in any of our organizations, from unit tests to black box, white box tests, in conformance tests, integration tests, systems tests, sniff tests, sanity tests. These days, of course, there's also COVID tests, but we're not going to talk too much about that. So the question comes to mind is, of course, what if exhaustive testing is impossible? That guy certainly looks exhausted. It turns out that in many of our reality, exhaustive testing is actually impossible. Even before you go to autonomous vehicles with non-autonomous vehicles, there's simply too many possible faults. Some are intermittent. Some are operating conditions that has a timing consequence that only happens. You can imagine the times when you bring your car in for servicing for some trouble, but it doesn't show up when you bring it to the dealership. It's so frustrating. You keep telling them it's there, but when they try it, it's not there. Autonomous vehicle testing springs up a whole new domain with machine learning algorithms and object identifications, which is now known to be brittle. We put a little bit of square tape on a stop sign and it stops being identified as a stop sign. And that's just a very simple tampering. Nuclear reactors can certainly have possible combinations of faults, which are staggering. Aircrafts can have huge effects from weather and human errors that are really hard to account for. And medical has very complex interactions with other drugs. And of course, spacecraft deals with the unknown. Besides the known unknowns. So what do we do? Well, it's already commonly known how to reasonably solve this problem. Obviously, you can't actually remove all possible faults. What you can do is build up something called a safety integrity level approach. And what this is, these are bins for levels of safety that is based on effects if the fault is not properly mitigated. What it's saying is that if the failure results in poor controllability, like you can't control the car anymore, and I use automotive constantly because that's the domain that Ilya and I do work in, as well as high performance computing. But so then you have to, then what that would demand is that it has to demand a low acceptable failure rate. So something that's uncontrollable has to be extremely improbable. We call that SIL4. Something that's difficult to control has to be very remote, and that has to be the SIL3. And those two most likely will result in death if your vehicle becomes uncontrollable or difficult to control. Something that's debilitating, it should be remote, and it's called SIL2. Something that's distracting, like maybe, I don't know, your wiper doesn't work anymore. That's unlikely, but it could happen. But you know what? If it does happen, it probably won't kill you. So it's a SIL1. And then finally, going down even further, there's a nuisance only type of controllability. Let's say, I don't know, maybe your headlight, maybe your door won't open or something like that. Okay, so that's kind of a problem, but it's a nuisance, right? You can maybe crawl through the window. So the acceptable failure rate is that, okay, that's reasonably possible, and it's SIL0. By the way, SIL0 is also something we're all fairly familiar with. It's also known as ISO 9001. Many companies go through ISO 9001 just to get through at least SIL0. And that's because most of the process that we go through don't need the higher level, but some do. If you're talking about braking system, that's probably right up there to SIL3 or 4. So the idea is that the whole thing doesn't have to be safe. We selectively demand certain amount of safety. So here across the top, you'll see that SIL1 has a probability of failure on demand of something like of 10 to the 2 to 10 to the 1. And it keeps going up to SIL4, where it's 10 to the 4 to 10 to the 5 probability. And the risk reduction factor for SIL1 is 100 to 10, whereas the risk reduction factor for SIL4 is 100,000 to 10,000. Now, then I follow on and list several different domains. So you have things like MISRA, automotive, aviation, and railway. Now, most of these, as it turns out, follows the general process, which has been encoded in 61508, the one in the middle. And other ones duplicate on top of that their specific levels. MISRA, of course, follows the general process of 61508 for SIL1, 2, 3, and 4. Automotive is very specific. They have automotive safety integrity levels, ASIL, and they have ASIL-A, which is just basically your QA, your quality of implementation. That's your ISO 9001 level, pushing all the way to ASIL-D at SIL3. Okay, so your braking system would probably be ASIL-D. Your wiper or your light might be at best SIL1. Okay. Many years ago, there was this unintended acceleration issue, and that's covered by something called electronic throttle control system, ETCS, and that's definitely in the domain of SIL3. I'll talk a little more about that. But aviation also has the DALE, except they go the other way, so it's DALD, E to D, C, D, and A. And railway and nuclear and medical all have them. I'm not going to list them all. So MISRA, based on these SILs, actually have specific guidelines for required practices at various levels. So I'll just walk through some of these. Specification and design. If you're at SIL1, the lowest level, you have to have structure method. If you're at SIL2, you have to add case tools on top of that. And then at 3, now you need formal specifications for those functions at this level. And then at 4, you have to have automated code generation when possible. Now, let's go to the second one, which is the one that many of us are more familiar with, languages and compilers. For SIL1, you need a standard structural language. For SIL2, you need a restricted subset of a standardized structured language, which is validated or tested compilers if possible. That's kind of where MISRA comes in. And SIL3 says it has to be same as 2. SRL4 says it has to be independently certified compilers with proven formal syntax and semantics. You actually have to do formal verifications. Okay, and then there's two more role that talks about what you have to do for your configuration management product and configuration management process. Now, I only took a few of these. There's actually a long list of other things that you have to follow for each of those columns. The key thing here is to note is that we think about this because in the world of safety, two of the big things that happen of concern is dynamic memory management and exception handling. And of course, in C++, and obviously exception handling defaults to dynamic memory management because that's one of the biggest issues of exception handling, among many other ones. If you've been to my SG14 study group, you'll know that we talk about both a lot. So what's the big deal there? Well, I show here that they're actually, in today's automobile, they're actually, in the past, the wisdom was you shouldn't do any dynamic memory management in the car. It should all be statically organized. In other words, after you turn the key, turn the ignition, you should not have any more dynamic memory access or creation. You can do it before you turn the key, but that's just simply not good enough today. As you can see in the picture, there are many, many places that is now doing memory management. We're talking about the Ethernet, the CAN bus, the cockpit computer, the ADAS, the pedestrian tracking system, and especially you're talking about convolution algorithms in machine learning that is using AI to do pedestrian detection and object tracking. There's just too many places you have to be doing dynamic memory management. So in other words, it's now everywhere. And yet, if you look at the two major rules governing automotive, one of them says, MISRA C++, says that dynamic memory management shall not be used. Now that was built in 2008. AutoSAR, which I'll talk a lot more about later on, says you have to allow it, but only under these very specific conditions. You have to be deterministic, make sure that it results with what they call WCET, bounded by WCET. You have to avoid memory fragmentations. You have to avoid running out of memory. You have to avoid mismatch allocations, and don't call anybody else that has non-deterministic natures to them. So how do you reconcile that? Well, I'm going to show you how we're planning to move forward with that. And this is going to be one of the major discussions going forward in terms of safety. So continuing on, I want to highlight one of the key things that is happening right now. And this is something that most concurrency and parallel experts, or especially concurrency experts, know, and that has to do with race conditions. It is simply when one CPU can have many tasks, and the task takes turns sharing the CPU and memory. And the concurrency defect comes when there's a timing difference at which data, there's some shared data in between that is both being read and written by both tasks. And there's such a timing difference between the read and write. I don't know, maybe one clock is faster or slower than the other, such that a write by task 2 here is overwritten by another write by task 1. Now, in a bank account, that can be disastrous because it means that if somebody's updating it, you could be overwriting the update, and now you lose the money that was previously updated because you were reading from a result that was previous to that update. So in days past and still today, one way to fix this is to disable interrupts before reading to ensure your task read-writes, only one task read-writes at a time. And if you don't do that, then you're going to get some subtle defects. Now, I don't know if how many of you guys were young enough to remember unintended acceleration. It certainly made a lot of history. This had to do with the fact that there were many calls by a couple of companies. I'm not going to name them names. You can look them up. That for some reason they were reporting that the cars would accelerate, the throttle would be stuck wide open, and even though people were not depressing the throttle at all. In fact, they were putting all their weight on the brake. They swear up and down that that's what it was. Now, I suffice to say that after numerous amounts of investigation, one by NASA, then another one, the court eventually awarded fines to the companies involved, and it all come down to the fact of this: that they noticed that even though they did not find a smoking gun, they find enough suspicions. Remember, this is not a criminal trial. The passing rate of a civil trial is a little bit lower. That there was enough evidence to point out that there were enough spaghetti code, which resulted in enough, which had a lot of shared global variables, and they were all accessed without being set to volatile, without the interrupt mask being set. So you read the bottom line, it says there are 865 users of interrupt masking in the code in 194 different source files. And this indicates the access to global variables is not always done under the protection of interrupt mask. And this has to do with the fact that the electronic throttle control system, ETCS, has both a CPU chip and a monitoring chip, and they would both interact with each other using global variables. You can kind of imagine how that works out. So in the automotive world, we have always known that there is stringent safety, and it's essentially governed by this document, ISO 26262, on road vehicles, functional safety. And in there, if you think there's nothing to cover software, you're wrong. There are specific work tasks that covers software in terms of control flow analysis, data flow analysis, static code analysis, static analysis based on abstract interpretation. You see that under the ASO levels, under static code analysis, it's a double plus, which means it is required, okay, that you follow ASO in this area. So let's step back and see, what does our community offer? Well, the two well-known guidelines. I'm going to step back and talk a little bit about the history. So the question that we're trying to answer is what's in the core guideline, or even MISRA C++ enough for concurrency, for concurrent safety? Last year, you saw a talk by me talking about MISRA sequential rule safety, and they're all over it. So here's the current state of where that is right now. The C++ core guideline, of course, is wonderful. It allows you to transition from legacy C++ code to modern C++ code. There's an underlying idea that it provides static analysis tools, ability to warn some violations, but also meta guidelines to improve efficiency, performance, and elegance. And the philosophy there is to write modern C++ code, okay? And it's supported by the guidelines support library, which I think is offered by Microsoft and Red Hat. And so that it allows you to do things like RA, II, but with things like finally, safe narrowing, contracts, span, okay? So some of these, so what are those guidelines? Well, those guidelines follow 11 philosophies. And these philosophies are quite important, and they'll be expressed throughout this talk, this conference. You know, expressed directly in code, ideas directly in code, write in ISO standard C++, express your intent. Ideally, a program should be statically type safe. Prefer compile time checking to runtime checking. And what cannot be checked at compile time should be checkable at runtime. Catch runtime errors early. Don't leak any resources. Don't waste time or space. Prefer immutable data. Encapsulate messy constructs rather than spreading them throughout the code. It also covers a number of areas, and I want to highlight the fact that of all these areas, concurrency and parallelism actually is one of the least complete section. Okay, it starts off with about 9 rules that is mostly meta-ish type of rules. Then it breaks into subsections for concurrency, parallelism, message passing, vectorization, lock-free programming, and etc., which is anything left over. So under concurrency, there's a fair bit of decent rules, some of them pretty specific. And then there's a whole bunch with question marks that have not been filled in yet because they don't know what to do with it, when to use a spin lock, when to use trilog, because there just has not been enough concurrency experts adding to these. So, and under parallelism, there's nothing. Under message passing, there are 2 rules and 2 unfilled rules on message queues and messaging libraries. Under vectorization, there's nothing. Under the etc. category, there are 2. Use volatile only to talk to non-C++ memory and something about signals. Under lock-free programming, there are about 1, 2, 3, 4, 5, and a whole bunch of ones that have no links to them, which means they haven't been filled in yet. They need somebody to fill it in. So if anything, this talk is also a call to arms to help with some of this. But I'll tell you what we've done, okay? So in summary, I just want to point out that while the C++ core guidelines have been great, you need to take them with a bit of a grain of salt, because there are some area that is still somewhat disputed, some editing required. But the one thing that I want to focus on is the fact that it needs more concurrency and parallelism. And this is what we're planning to do. So C++ undoubtedly is a complex language. Beyond himself says that C makes it easier for you to shoot yourself in the foot, but C++ makes it harder. But when you do, it blows your whole foot away. Well, there are these many things that could be potentially adds to the complexity. I'm not going to go through them. I think you kind of can pick out your favorite amongst there. Now, stepping back to see what are the safety critical guidelines, I enumerate almost most of the ones that I know. I know there might be one or two missing, but here they are. I highlight in red some of the most recent and probably the most valuable ones that are still being tracking to the latest standard, like MISRA C and C++, AUTOSAR C++ guidelines, and C++ core guidelines. The rest have slowly fallen off because they either track to an older standard, they're not being updated. Okay. On the right, I track a bunch of standard that is related, but not specifically to coding. So some of these standards have different intended target audience. For instance, MISRA are checkable rules only. They need to they have rules that are automatically statically checkable. This is valuable because in a large code base, you can't actually read the whole code for all the violations. You need something that's automatic. AUTOSAR C++ is a mix, and C++ core guidelines is also a mix. Okay. So which one to choose and what is the difference? Well, because of the various different stage of the guidelines, if you want safe but not C++ 11, 14, or 17, well, you can either use the Joint Strike Fighter, which was done with the help of Beyond Strelstrup, or you can use MISRA C++, but it's based on 2008. But it, unfortunately, because of its popularity and the fact that it was nearly the first, it continued to be the reference for every other safety guidelines going forward. They all reach for that old standard. But it's good in that it allows you, but many people still use it because in the embedded world, compilers don't move that quickly. So until recently, there has not yet been the massive outcry that's been required for them to update, because people are now finding even the embedded compilers are moving forward to C++ 11, 14, and 17. But in the meantime, for their code, that is, they provide automatic static tools, okay, and aiming to the embedded domain. Then the one on the right are the C++ 11, 14, 17 that's reasonably up to date, but they're not safe. So like high integrity C++, like certs from CMU, the core guidelines. Core guidelines is actually unique in that it's actually tracked to almost to the latest standard, and it keeps moving. And WG23, a working group within SC22, is trying to track programming vulnerabilities. And that's meant to be for team leads who might not know this language and they need to scan quickly and build their own guidelines. There's one that is both safe, but only up to C++ 14, and that's AUTOSAR. But it's not being updated anymore, because one of the effort of our group was to try to make sure that we don't end up with two safety guidelines. We were able to merge AUTOSAR and MISRA so that it ended up, everything is now in MISRA in their next update. Ilya is here because he actually worked on the original AUTOSAR standard. So comparing coding standard, in this one slide, you can see that AUTOSAR is C++ 14. It doesn't have any parallel sections. MISRA was C++ 03, but we're working towards something that might cover C++ 17, no parallel sections. High integrity C++ is C++ 11. It has some parallel sections. Joint JSF is C++ 03 and it has none. C++ core guideline is basically tracking whatever is the latest, and it has some parallel sections. And the cert C++ is tracking the 14, but it has very few rules regarding parallel and concurrency. So let's look at MISRA and why MISRA. Well, MISRA essentially, here's the origin of MISRA. Originally, when Ford and Jaguar Land Rover in the UK asked to create something that would work in C, so that's when 1998 MISRA C was created. That became the input to JSF to some degree, a minor degree possibly. And then JSF became the input to MISRA C++ 2008, and something from the UK Ministry of Defense, and along with the next revision of MISRA C. MISRA C is now up to MISRA C 2012, okay? And this is a list of some of the adherents right now. There's the MISRA C has been revised 1998, 2004, and then 2012. And then MISRA C++ was last revised in 2008 with 228 rules, of which 219 of them are statically enforceable. And many compilers make their money on this, selling it to you. You knew there was a commercial angle to that, but I'm not involved in it. C++ in safety critical, there are many things that are good, and there are many things that we inherited from C that are loopholes that has to be covered by tools like MISRA tools, preprocessor, undefined language, undefined implementations, and type system, multiple inheritance, and dynamic memory. On the good side, C++ is undoubtedly good in the fact that it supplies you with OAII, compile time polymorphism, regular types. You might wonder why I think exceptions is good, because I do. Exceptions, both C++ is suitable for both exceptions and error codes. Tomorrow's talk, when I talk about embedded programming, I'm talking more about that. But as being the chair of SG14, we've come to the conclusion that C++ needs both exceptions and error codes. I mean, how are you going to report errors coming out of constructors and operators, right? If not for exceptions. There's smart pointers. Lambdas is good for safety critical because it allows you to throw away that lambda to a separate thread in a value capture so that there are no dangling. Then there's parallel algorithms, and of course 20 comes with contracts and concepts. C++ is moving in the right direction for safety critical. So just to give you an idea about some examples that need safety net, I can't actually show you examples from MISRA because they are copyrighted. I shouldn't even be showing you the actual headlines to some extent. But you can see that what they're looking for is to make sure that if you have an if-else, you have braces properly enclosing them so that somebody can't intercede a line following the else accidentally into the if-else. That's most of these sections, the selection statements is talking about. What kind of conditions, and switch statements and things like that. And certainly in the type system, this is one of the loopholes, because C++ standard doesn't define fixed sizes for built-in types. It makes it hard to write portable code requiring fixed size integer. Now, that's obviously being addressed and being fixed right now. There are quite a few SG14 proposals in that direction, and I'll talk about that tomorrow. So C++ does all the arithmetic operations in either int or long, depending on the original operand. So here, in this case, this can... because of the promotion, this can easily lead to non-portable code. So here in the following here, on a system where int is 32 bits and short is 16 bits, the result's going to be 80,000. But as one would expect, considering that the multiplication is going to be carried out and both operands promoted to int. However, on a system where int is just 16 bits, the results will be undefined because the multiplication is going to be carried out in 16 bits, and the result, carry on 6, and then there will be an overflow. And so then only the wrong result will then be converted to int32. So this is this is what the MISRA will try to help you to identify. And then it's up to you whether you want to fix it or not, because they have different levels, which Ilya is going to explain. So let's look at the pedigree again. C++ was safety critical API. In C++, in 98 and 03, we got things like inheritance, exceptions, and template STL. And based on that, we built MISRA 2008, which came in C++, which covered 98 and 03. Then 11, we got things like auto, lambda, concurrency, move, and futures. And all through that time, there's been no update to MISRA. However, and that's when AutoSAR came in and said, hey, look, guys, we really need something that covers more recent C++ because the embedded tools are moving up. So they got something that covers C++ 14 in 2017. But by 17, we already got things like template deductions, compile time if, parallel STL. So in 2019, our group moved to help AutoSAR join with MISRA. Remember, AutoSAR actually came to this conference once or twice asking if we wanted to take over that standard. And the C++ standard said, no, we're not doing it. This is not part of our job. But there are people out there who are good at these kinds of jobs. And so MISRA and AutoSAR amicably agree that this should be a joint committee. So in 20, we're going to get things like modules, concepts, coroutines, and ranges. And so the next MISRA that comes out will be joined with MISRA and AutoSAR. And it could be aiming for C++ 17, I hope. There are many of our current committee members are now joining MISRA. When I first joined MISRA, it was like 5 people. Now there are 15 of us. 10 of us are actually from the C++ standard commit. So I think we're hoping that that will result in a much stronger standard. So what's still missing in the safety guidelines? So far, mostly only deal with sequential code, as you can see. There are very few that deal with parallel code. Even fewer deal with concurrent event-driven code, and none of them actually deal with heterogeneous dispatch. And the rest of this talk is going to show you a path that we hope will lead in that direction because the industry badly needs it. As a reminder, this injection of safe concurrency rules is a work in progress. And many of these rules have not been merged yet and can still change. And this is why we can talk about it, because they're not in MISRA yet. So Ilya and I can actually talk about these things. However, we are actually highlighting this so that calling it out so that if you want to give your feedback on what you prefer as a safety rule, you could certainly join our group. So at this point, I would like to turn it over to my colleague, Ilya. Thank you.
Okay, so why concurrency and parallelism? Autonomous driving vehicles require more and more computational resources, and this is why highly parallel, concurrent, and heterogeneous systems come in. We will need more machine learning algorithms which will detect objects in real time and for trajectory planning as well. Many edge devices, such as medical devices, will need to do real-time safe decisions. Drones are also flying and are part of safety rules regulations. So with that, we need more and more concurrency and parallelism rules. We started this effort around 2 years ago, and currently this is a list of people who are involved in that. There are Workgroup 21 SG1 members. There is a Workgroup 23 parallelism vulnerability members here, and here is the list of individuals which are currently actively working on this set of rules for parallelism. Here you can see the screenshot of the table of contents for the current document which we are working on. This is just to give you an idea how we are working on. And with that, we came to the 81 rule as of now within 9 sections. We have a dedicated section for threads, for mutexes, for conditional variables, for atomic, for future, for volatile operations. We have more meta rules for lock-free programming, general parallelism, and interaction between the tasks. This effort mainly is driven by the idea that some specific rules will go to MISRA and Workgroup 23. Some meta rules will come to C++ core guidelines with the help of Workgroup 23. And we also finding some defects via cross-checking of the rules and the current C++ standard, which we actually go to fixing to Workgroup 21 draft. The rest of the talk will be focused on demonstrating some specific rules which are decidable or hard decidable, some meta rules, some rules which fit better MISRA guidelines or core guidelines, some rules which are wrong or that show defects in C++ standard. General rules in MISRA follow this following structure. There is a key rule statement which describes the essence of the rule. There is a category, mandatory, required, or advisory, which explains how much efforts you should put to avoid using this rule in your code. Within mandatory category, you are not allowed to violate the rule. In the required category, each violated rule will require a specific written deviation in your safety case. within advisory rule, you have more freedom to avoid using this rule in your specific code. The next thing is analysis. It shows the rule from the perspective of static analysis tool. Whether it is decidable or undecidable means if your static analysis tool or some static analysis tool can possibly detect this thing in the code. And within scope means whether single translation unit is enough to for the tool to understand that the rule is violated, or the tool should have a visibility on the application level. Rationale gives the reason for this rule to exist in safety case. Some rules have exceptions where the rule is not applicable in certain cases. And almost any rule has an example of the code which is compliant and non-compliant with the given rule. Here is an example of the rule from the thread section. Do not call std_thread detach function. The main reason for this rule is the analysis of the lifetime of the resources connected with the thread is much more difficult when the detach is used. This is why the category for this rule is required, meaning you need to write a formal deviation within your safety code and provide the reason why your code is still safe. It is decidable. That is, if the static analysis tool finds the call for thread for detach function, it means the rule is violated. And it can be done on the level of the single translation unit. The tool doesn't need to know anything about other parts of your program to understand that here the detach function is called. The rule has different sources. Core guidelines have a don't detach a thread rule. Core guidelines, high integrity C++ rules, and the C++20 have somewhat connected rules about using std thread replacement, which will join on the destruction. Here is another rule from the mutex section. The order of nested locks shall form a DAG. It is an example of the rule which is theoretically decidable, but tool will need to observe the whole code base to understand whether you have a violation of this rule. This rule has roots from high integrity C++, where it is almost exactly the same. Also, cert rule has a very similar nature of avoiding deadlock by using locking in predefined order. Here is an example of another rule. It is almost meta level rule. And its source is C++ core guidelines, where the rule was think in terms of tasks rather than threads. A very meta description. We translated this rule into the more specific do not use std thread in order to try to push people using higher level APIs, such as std async or algorithms with execution policies, parallel or paransec. This rule is of advisory level, so if you still want to use std thread, you don't have to put too much effort to explain why in your safety related project, it is easy to detect by the tool, but it has a specific exception. If you're accessing native thread handler to do some specific specific work, such as changing the priority of the thread, then this rule becomes non-applicable. With that, static analysis tool will need to detect the access to the native thread handle in order to accurately fulfill and check this rule. And here is an example of the rule in the atomic section, which we currently have a significant debate on. Use only STD memory order sequentially consistent for atomic operations. We have more or less agreement that it is a good rule, but there is ongoing debate of the category for this rule, whether it should be mandatory or required or advisory. There is also many use cases where there is a reason to use more relaxed memory orders. With that, there is ideas to put a set of exceptions that in certain cases, in order to get more performance, you may use other memory orders. But with that, if we put all these exceptions in place, the rules becomes non-decidable. Because the main problem with that, all these exceptions apply when there is when the user have some intention which is non-visible to the static analysis tool. Here's another example of the rule which we looked through from C++ core guidelines and dropped. This is don't use lock-free programming unless you absolutely have to. The reason from C++ core guidelines was it is error-prone and require expert-level knowledge of language features. Core guidelines have an exception of using atomic variables in this case, which makes these simple and not require expert-level knowledge. We looked at this rule and decided that it is too meta-level for considered at MISRA level, and there is no any chance to make it decidable. And with regards to atomic concern, it is already discussed in other sections of the considered guidelines. So with that consideration, we dropped this rule from our scope. And the next one is an example of the rule which we may consider as a reason to review the C++ draft, since it may have some issues, and Michael can explain better.
Thank you, Ilya. So actually, I want to go back to this particular rule. The core guideline wording says it's error-prone and requires expert-level knowledge. No, it's not. Lock-free programming is not error-prone. It's people who are error-prone, actually. So with that, I want to cover this one. Thanks to Paul, McKinney, and Megan Michael, we've been working this rule, and it says that there shall be no code path which results in locking of the non-recursive mutex within the scope when this mutex is already locked. Now, this is just common sense, right? If you're using a non-recursive mutex, once you start the lock, you really shouldn't have another lock going, okay, on that same thread. The question comes in is that further on under rationale, they also try to push speculative locking to say that you shouldn't speculatively lock it either. And so you shouldn't call things like try-lock or any of the timed try-lock versions like try-lock for and until and things like that. So that made us look deeper into the standard because try-lock really has only two possible states. It can either succeed or it fail. So when we looked at the standard under thread.lock.unique locking, it actually says there are two possible error conditions, which we think doesn't make sense for this particular case for trilog. Then we started looking at trilock until, which is possible. You could do a trilock until inside of a non-recursive mutex. Okay, fine, I can accept that. But when you look at the errors in trilock until, none of it has anything to do with timing. It seems to be a copy and paste from the other sections. In fact, that copy and paste happens everywhere. So I need to discuss this with my colleagues and friends in SG1, and then to decide whether we should just go ahead and file a bug on something like this. So as you can see, our exercise of walking through, and now we're almost like about 2/3 done, but that's only the first pass, which resulted in a lot of discussions, and we need to go back to do a full second pass and maybe a third pass before we can even release these rules to the world. But here's the thing. So what is still missing in these guidelines? Okay, we already said that there's very little out there that covers safety of parallel and concurrent rules. And we showed a work in progress of where we are right now. And we're hoping that many more people will join who's interested in building such safety guidelines for safety critical cases like aviation and automotive. But you'll notice that none of this deal with heterogeneous dispatch code still. That's another level that we still have to deal with. Now, I'm also involved in Chronos, and Chronos do have a bunch of safety critical GPU-like APIs, like OpenGL, and there's safety critical versions of those. And they also have Vulkan, and there's a safety critical version of those. And the idea there is that largely those are using MISRA rules to be applied to the APIs. And because those APIs tend to be older, they can use the current MISRA. But SYCL, on the other hand, is modern C++, and we need these MISRA rules to be updated so that we can apply them in general so that they can be combined with ISO 26262 and the other standard that I'm working on, which is SOTIF, safety of the intended functionality, ISO 21448, which is safety for autonomous vehicles so that we can build a language that hopefully will be safe and build other languages that will be safe. Not just SYCL, maybe it's CUDA or maybe other ones so that we can help to make sure that every language out there has a safety component. So where are we? Well, the present state is that MISRA C and C++ remains the de facto coding standard for automotive and the base upon which others are built. In fact, it's not just automotive. MISRA is now really for almost every embedded cases. And what is embedded? Well, that's a big definition that I'm going to talk about tomorrow. MISRA has been integrated with AutoSAR. That's at least one thing we can be proud of, is to reduce the number standard by one, not have many more proliferated standards that just confuses people. I've hated that since I was involved with OpenMP and all that. So, I never liked more than, multiple standards, although invariably that seems to happen. But there's still work needed to add additional features from C++ 11.14 and 17. What that means is that even when the new MISRA comes out, we will still be missing some amount of features from 11.14 and 17. Mainly, that's mostly we just don't have enough hands. But we are getting more and more hands now, but it's still not enough. We have calls like almost every Friday at 6 a.m. in the morning for Eastern time. So imagine what this will be like for Pacific, because this is mostly driven from the UK. So we lead the effort in MISRA and SG1 WG23 to add parallel concurrency, and hopefully in future to heterogeneous support. And the whole point I've been interested in this is because I've been trying to drive SYCL in that direction to have safety so that it can work for safety critical applications. So the conclusion coming down, we're getting down to close, and I'll be able to address some of the questions. Some of these questions are really good. The world has been building safe sequential programming rules, and even that effort has been constantly behind the ratified standards. There are very few safe rules for concurrent programming right now. And these bugs are extraordinarily subtle. And the world is transitioning to parallel devices, even in non-self-driving cars, never mind autonomous vehicles. And most domain experts are not C++ experts. And few of those are concurrency experts. So they need us. They need people like you and me and Ilya, who are concurrency experts, with somewhat of concurrency experts, to talk about what it takes to make C++ safe in that domain. These autonomous vehicles are pushing the boundary with machine learning algorithms for object recognition, detection, and tracking. So we're building safety rules to augment MISRA and core guidelines so that both can benefit. Core guideline could be benefit with the meta rules as well as the decidable rules, some of them, whereas MISRA is mostly just looking at things that's decidable, that can be done automatically. So please help us and join our effort. I'll close by saying that I like to envision a future where AutoSAR has already merged with MISRA, and then coming out of this MISRA effort, it will go to ISO C++. Some of these rules might in fact encapsulate into actual standard text, and some of it will go to the core guideline. Others will go to the safety critical groups that are involved in kernels like OpenCL, Vulkan, and SECL. So with that, I think that's my last slide. And I'm going to head toward taking questions. I'm going to ask Ilya to come back on. So the first question is really good. Is a complete ban on dynamic allocation too limiting for modern software systems? And how can someone prove that custom allocators meet the AutoSAR guideline? I want to say that without categorically that you cannot ban dynamic allocations in modern software systems. You have to allow it. The question is, so MISRA, I think, has accepted that, that slide where we showed. MISRA will probably head towards changing their rules so that it's instead of a complete ban, I think they'll take some of the AutoSAR rules. The problem is some of those AutoSAR rules are hard to meet. For instance, guaranteeing that you will never fragment, guarantee that you will never run out of memory, guaranteeing that you will fit a certain WCET, worst case execution time. Those are difficult parameters to go through. I think I know of a few libraries that actually can work for no fragmentation and no errors, but other ones are going to be hard to get to. I want to hear what Ilya's thought is there. He was actually one of the people that was in AutoSAR that dealt with this particular area. I'm just going to go back to that slide if I can. Go ahead, Ilya.
Well, from my side, I can add that there is almost no chance that system malloc can fulfill all the requirements of AutoSAR. But the reason here for this rule is that you should consider that those aspects of the malloc will fail, and you should have a plan for the case where when it fails, what the system will do, and how it will detect that, and how it will handle that. And reasonable approach for that is when the malloc fails, you can just kill this process and restart it and start from the scratch. There are other things you can do with that, but the main reason for this rule in AutoSAR to exist that you should analyze all these aspects of the application and consider plan B.
Very good. The second part of that question says, how can someone prove that custom allocators meet the AutoSAR guidelines, assuming those AutoSAR guidelines also become MISRA guidelines?
There are certain custom allocators like monotonic allocators or pool-based allocators where you can almost prove most of these aspects of the AutoSAR rule, but it is not the silver bullet allocator for all the cases. It is the specialized allocator for your specific use case.
Yeah, I remember talking to John Lako that monotonic, the one that's monotonic allocator can do most of this, but it's still not the complete picture yet. And I would like to push for certain types of allocators that can satisfy this complete list. So I think that answers that top question. The next top question asks, how can we take advantage of those safety guidelines in user applications? So by that, I mean the safety guidelines that we're building right here. If you talk about the concurrence guideline, the sequential guidelines, there are already tools out there by Perforce, Synopsys, Coverity, LDRA that already do those things. They will generate thousands of these errors for you. In fact, that's what they did with the unintended acceleration. They ran their code and found something like 10,000 errors, that 10,000 advisory or issues. For the sequential guidelines, these have not built into the tools yet because we're still debating it. and it will probably be a year or 2 years before we can materialize them in the MISRA standard. But you can certainly have a look at it. I'm not making it like restricted or anything, and you can certainly. I'm hoping that will actually galvanize you to help improve it and help us. But right now, the only way is if you follow the guideline by eyeballing it, or build some sort of tool. But the whole point is that this goes into MISRA, and then MISRA creates the tool. The MISRA tool vendors create automated tools for it. They are also on board. They are always asking us, is this checkable? Can you check this? Obviously, with a lot of things, if we're talking about intentions, like double check locking, it's just really hard to tell somebody's actually using double check locking, right? That is essentially banned in the MISRA's concurrency guidelines right now in our document. But it's just really hard to tell somebody's actually using that, right? So you can't really easily ban it, right? So, Ilya, did you want to add something? I think.
Probably no.
Yeah. Okay, that takes care of that. Next question says, what efforts exist to shape the design of the C++ language based on these safety considerations to take a more proactive approach to ensuring safety? Really good question. I'll take a crack at answering that, and maybe Ilya can help. So yes, part of our intent was always to feed this back to C++. And there are several groups that is possibly the right place for that. There is SG12 on vulnerabilities and undefined behavior. There's SG14 on embedded. There's this proto group that has been starting on safety critical, which people have been talking about either starting their own group or adding that to SG14. I have no personal position on that, but we recognize that it would be possible if we could add some of these prohibitions back into C++ standards so that you don't have. But I think the reality is that you will always have to have some that's in a tool and some that is in the standard. Okay, you cannot. The C++ standard, I'm speaking now with my directions hat on, is not specifically, as much as I'd like it to be, it's not specifically there to serve the safety community. It's there to do performance for high productivity. Some of it is high performance computing. Some of it is just good old manufacturing, banking, games. So it needs to be able to serve a wide community. So as such, I can say that while it might be good to segment some features towards the C++ standard, it will be necessary to keep some of that in the tools, because some of it I just don't see the C++ standard accepting, because it would just limit the performance significantly for other domains. Ilya, did you want to?
We also consulting with different people from several work groups in work group 21. So the work through individuals is also work in progress.
Exactly. So we only have about 3 minutes left. So I'm going to take one more question. How to get involved? I have an email in the slides. You can easily find me, obviously, and you should be able to easily find Ilya. And we are basically having a call every month on this stuff. And I will give you this link to this document so that you can get involved. Right now, it's not restricted to MISRA, because even though the aim started in MISRA, I've opened it up sort of so that it's now available SG1 to pretty much everybody. So that we can have, as you can see, the guest list has been quite large. Ilya and I started this, and then Bogdan from NVIDIA joined. A bunch of people from LDI and Perforce joined, as well as people from AutoSAR, Jaguar Land Rover, QNX. So yeah, there's just get in touch with us, and we'll happily try to get you involved. Okay. 10 seconds left. I don't know we're going to be able to get through to the last few questions, but there's one here on FMEA and FTA analysis that is extremely interesting that I'm going to have to make sure that I keep, and then we can save those answers so that we can relate them, because we are involved with all of those system theoretic process STPA analysis techniques through through the ISO 26262 and 21448, as well as UL 4600. So let me see. I think that's we should stop here. Thank you very much once again for myself and for Ilya. It's been wonderful talking to you about this. This is one of our favorite topics, and we hope to engage with you somewhere, sometime. Thank you. Cheers, guys. Bye-bye.
Bye.